Hello, Science 30s. So in our last video, we learned about gravitational fields, and now in this video, we're going to be learning about the electric fields. And so if we take, first of all, our textbook definition of what an electric field is, it is a property of the space around a source charge that enables the source charge to exert forces on other charges that enter this region. And so you've noticed really the big difference between an electric field and a gravitational field is this word charge. So there are, instead of with our gravitational field, it was masses. Now it is charges. And we need to understand that there are positive and there are negative charges. So I've attached a picture there from their diagram from the textbook, and you'll see positives and negatives kind of all over the place in this diagram. We have a cloud up in the sky, and that cloud, the important thing to realize on this cloud is that at the bottom of this cloud you see largely a lot of negative charges. And relative to those negative charges along the tops of trees and the tops of houses, and even if there was ground here, but these are all the higher things, these are all relatively positive compared to the negatives that are building up here. And I guess we should go over very quickly here the fact that negative and negative repel, positive and positive repel, and positive and negative attract. And so there's starting to become in this storm that's about to happen in this picture, there's starting to be an attraction happening between the cloud and these positive spaces that are building up here and this negative bottom of this cloud. And so that is how lightning happens, is you get this negative charge on the bottom of clouds, you get this positive charge on everything else, especially the higher up things. And again, that's a relative difference. And again, it comes down to the movement of electrons. So here what we're talking about is the movement of electrons. And obviously with a lightning strike, there is a lot of electrons that are moved. And so so I guess before we get into the formulas of this, I do want you guys to understand a little bit about what this looks like. So in words, field lines are going to point away from positive sources and towards negative sources. So again, what we're talking about here is the movement of electrons. Electrons are moving towards the negative spaces. That's why they're negative. More electrons, more negative. And so that's the way we're going to draw our fields as well. Our fields are going to be drawn with that in mind. And so if we have one source right here, which is positive, and we have another source here, which is negative, just let's assume these two are not interacting with each other right now. We would just say that the electrons are moving away from here. So electrons are moving always going to be away from a positive source. And this particular source right here, which is negative, is going to have the arrows moving towards it. So the electrons are moving towards it, which is why it has that negative charge. So if we go back to our diagram here now with our house and our trees, which are relatively positive, and we go back to our cloud, which is relatively negative, there is going to be a lightning strike. That lightning strike is going to, by our eyes, all that we see is it goes down, but our field lines are actually going to be moving up, because that's where the flow of electrons is happening. The flow of electrons is again going towards that negative space. And so again, it would be an infinite number of lines. I'm not going to draw an infinite number of lines, but there we are. So it's going to be right from those positive sources into the negative ones. We'll now get into into a discussion on the formulas that are involved with electric fields, and we'll be done for electrical fields video. So the one formula that you need to know for electric fields is right there, and I have the data booklet there, page 2, right in front of me as well, and so you can see. So what we have is we have this E with lines right here, vertical lines surrounding it, and that is the electrical field strength, or electric field strength, and that is going to be in newtons per coulomb. We'll talk about coulombs in a second. So first of all, what these lines mean, these lines are absolute value, which means if you're given a charge of -4, you just note it as 4. Okay, you just the negatives and the positives do not matter when we're talking about this. K is going to be Coulomb's constant. Just like we had a big G, we have a constant in electric fields as well. And so electric fields, the constant is going to be 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Then we have Q. Q is the number of coulombs right here, the electrostatic charge in coulombs. And coulombs is just a way to measure charge. And those numbers are usually quite big or quite small. And so then we have r, and then which is again just like gravity, we have r squared, and so that's your radius in meters. And so we'll jump into our first example. In example number 1, we're just going to be looking at 1.6 here from the textbook, and we're only going to be doing A. I'm not going to get into the other formulas for electrical fields because they're not in your data booklet. So we're only going to do formulas that are in your data booklet. And the first, or the formula that we need to know here is again what we just covered up there. So now we need to define our variables. And the first one that we have is the Q. Q is given to us right here. So one of the charged spheres being developed to protect a base on the moon has a charge of 0.0200 coulombs. Determine the strength of the electric field 20.0 meters from the center of this sphere. And so one thing we'll notice, the distances in electric fields are often much smaller than the distances in gravitational fields. And yeah, you'll notice that for sure. So let's get into this. So for A then, which is the only one we're doing here, Q is going to equal 0.0200 coulombs. That is positive. We'll just put that in for right now. And we also have the fact that R is equal to 20.0 meters. And we are supposed to be solving for the strength of the electric field. And so the electric field strength, again, just use your data booklet, guys, it's right there, is E. And so that's what we need to solve for. The other thing that we have to define here, obviously, is our constant K, which is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And now we again just jump right in and do this formula. So we have the electric field strength will equal KQ over R squared, which is going to equal 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. We're going to multiply that by Q, which is 0.0200 coulombs, and we are going to divide that by R squared, which is 20.0 meters, and that has to be squared. Do not forget to square it. And we get a final answer here of 449,500 newtons per coulomb, which, if we take to proper sig digs, is going to be 4.50 times 10 to the 5 newtons per coulomb, and that would be the strength of this electric field at the at this potential moon base that they're talking about in this question. The next example that we're going to do is 1.7, and again, that's from the textbook, so you guys can take a look at that if you want. And what we're going to be doing here is figuring out the charge on a balloon. So a balloon is given a charge of negative 4.5 nanocoulombs. A, determine the strength, electric field strength, 30 centimeters from the center of the balloon. And B, sketch a diagram of the electric field lines around the balloon. So, first of all, so A, we have the charge given to us. Q is equal to negative 4.5 nanocoulombs. If you use the first page of your data booklet, you will find out that nano means times 10 to the negative 9. So this is negative 4.5 times 10 to the negative 9 coulombs. Remember, we cannot be in nanocoulombs. We need to be in coulombs according to our chart there, or our data booklet. And then the next thing we have is R, which is equal to 30 centimeters. Well, once again, that needs to be in meters. So we know that 1 meter is equal to 100 centimeters. And so we are going to times this by centimeters on the bottom, meters on the top, so those cancel out. And so we're essentially dividing by 100 here, which is going to equal 0.30 meters. And I'm not going to define K in this case, we already did. So I'm just going to go right into the formula here now. E, electrical field strength, is going to equal KQ over R squared. RK is going to be 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And we're going to be multiplying that by negative 4.5 times 10 to the negative 9 coulombs, and then dividing that all by 0.30 meters squared. And we land up with an answer here of 4.5 times 10 to the, I think it's 2 newtons per coulomb. So a couple things here I want you to notice is that there was a negative up here. And so why are we not negative down here? And the reason why is because of this value here is absolute value, so we would just get rid of the negative. So even though your calculators show this answer as negative, when we write it down, because of the absolute value, we just do not include that. And the last part of this is sketch a diagram of the electric field lines around the balloon. And so I have drawn a balloon here because I've learned never to draw things live. It never works out for me. So here's our balloon. And I guess what we have to realize here is that the balloon has a negative charge. The balloon has a negative charge. That came right from the question. The Q is negative. Doesn't matter what the electric field strength was, the Q is negative. So because this is a negative source, we know that the field lines then are going like this towards this balloon. And that's it. That's all we need to show for our balloon and our electric field strength and the directions, the field lines. And that's it for electric fields, guys.